All right, advanced math A, here we go. We got lesson 10.1.1, association in two-way tables. This is day one of this lesson. We'll pick up day two on Monday. So anyways, last semester we looked at associations between numerical data. So like we did stuff like, remember the pizza one, where we had like the number of toppings and like the price of the pizza. Those are numerical data. You know, money is numbers. We also did that one where we're looking through the hole to see the football game. So we were looking at distance, we were looking at width, we were dropping the ball, so the bounce height, we were looking, that's all numerical data, like distance, height, weight, price. They all have a number associated with it. In this unit, we're going to look at something called categorical data, which doesn't necessarily have numbers associated with it, like your hair color or your gender or what classes you're taking, your favorite restaurant or things like that. They don't have a number associated with it. Maybe like if you had like the number of people who have brown hair, there's where you would associate the number, but the data itself, the category doesn't have a number with it. So we're going to use probability instead of the regression models to look at whether the data has association between it. Remember, associated events are events that kind of cause each other to happen. They're events that are related and that one event makes the other event more likely to happen. Whereas mutually exclusive events, which we really haven't seen too much before, those are two events that can't happen at the same time. So like I can't be on vacation and be teaching at the same time because teaching is no vacation. So those two events can't happen at the same time. We would call those mutually exclusive events. And certain events just can't happen at the same time. And then we have events that we call independent events. These are events that happen at the same time, but unlike associated events where one is kind of associated with the other one, it kind of causes the other one to happen or makes it more likely to happen, independent events are, well, independent. They just don't happen. They don't affect each other. So they happen at the same time, but don't affect each other. So just as a review, you've seen Venn diagrams before. And Venn diagrams usually have like two circles or something. In class, we kind of had people raise hands and we said, okay, how many people just own a cat? And like I think one of the periods said, oh, 5 of us own a cat. Oh, yay, 5 of you own a cat. Sweet. And then I said, okay, how many of you own a cat and a dog? Okay, so then there was like, there's 7 people. Okay, we own cats and dogs. Yay for you. Good. Okay, then we said, okay, how many people only own a dog? And they're like, oh, there's 11 of you. Oh, sweet, 11 people, yay. And then how many neither own a dog nor a cat? And there's some people in there, and they're like, 12 of us. We don't own cats, don't own dogs. Hate animals, woo, whatever. So then I asked the question, okay, so according to this, how many people own cats? And some people said 5, and that's not correct. 5 people only owned cats. But then there were 7 more people over here that owned a cat and a dog, so we would have to include those. So the total number of people who owned cats would be 12 right there. And the total number of people that would own dogs would be 18 right here, because we'd have to do this and portion here, this overlap. We'd have to count those because they go with the cat owners and they go with the dog owners. Now this brings up a very dangerous part of doing Venn diagrams, is double counting. So like if I wanted to add up the cat owners, which are 12 of them, and if I wanted to add up the dog owners, which is 18 of them, and I wanted to add up the people that owned neither, so this ends up being 42 people total. But there are not 42 people in the class. If you add up all these other numbers, you find out there's only 35 people in the class. So how am I getting 42? Well, when I add up the cat owners and the dog owners, I have just double counted these 7 people. Because these 7 people are included in both cat and dog owners, that makes us overcount. So sometimes we have to subtract out that double count so that if I subtract out the 7 from here, I get to the 35 people that were actually in class. So really be careful of that double count. The verbiage is really important here. If I say only cat owners, yes, that's 5. But if I say cat owners, it's 5 plus 7, it's 12. All right, moving on. Okay, Keon is conducting a survey for the school newspaper. He surveys 175 students. That's his grand total, 175. Now he finds out that 28 students have the new PiPhone, and who doesn't want the new PiPhone? 44 of the students had a laptop, and 110 students had neither. So let's make this circle the PiPhone. These are the PiPhone owners. And let's make this circle the laptop owners. That would mean that this would be PiPhone and laptop. And then this section here would be neither the PiPhone nor the laptop. We already know that's 110 because it tells me right here. Now, the mistake that a lot of people make is they go, oh, 28, that goes here. And 44, that goes here. But if we do that, let's see what happens. 110 people with nothing, 28 students with a PiPhone, 44 students with the laptop, and add those numbers up. Do you see what we're getting there? 2, carry the 1, 8, 1. We got 182 people. Wait a second. There's only 175 people that he surveyed. What does that mean? It means if I take 182 and subtract out that 175 people, we are double counting 7 people, which means that's the and portion. Those are the ones where it has both. So now when I talk about the 28 people with a PiPhone, 7 of them also have a laptop, but 21 of them don't have a laptop. So now I've got 21 with the PiPhone, 7 with the laptop and a PiPhone. That's a total of 28. And then the 44 students who have a laptop, I'm going to have to put 37 here because 37 plus 7, that's 44. It's the entire circle that includes all the people with the laptop. So we've got these that are double counted in here, so we need to break that out. All right, so how many students have PiPhones or laptops? Well, these 21 have a PiPhone or a laptop. These 7 have a PiPhone or a laptop. These 37 do. So basically, if I add up 21, 7, and 37, that's how many have one or the other, or even both. And that's 65 students. Why can you not just add up 44 and 28? Because up here it said that we had 28 students with the PiPhone, and we got 44 with laptop. Why can't I just add it up and end up with 72 students? And again, it comes back to that overlap. If we just add these two, we are double counting these 7. So we can't double count, which you could just take 28 and 44 and subtract the double count, subtract the and, or just add up these 3 numbers together. So we can't just add those 2 numbers because we would double count the PiPhone and laptop owners. All right, 10-2. Abigail doesn't like the Venn diagram. Instead, she prefers to do a 2-column or a 2-way table instead. So we have the same types of numbers here. It looks slightly different. So she has laptop, not laptop, PiPhone, not PiPhone. So laptop, it said there were 44 people who had a laptop. So these are all the laptop users or owners. Here's all of our PiPhone owners over here, 28 of them. Here's our grand total of 175 people that were surveyed. And then here's the 110 people, no laptop and no PiPhone. Now the nice thing about the 2-way table is we can easily, a lot easier, that's not good English. Anyways, it's easier. Let's just go with that because everything has to add up. So if there are 28 people here who have a PiPhone, that means that there are 147 with no PiPhone because these 2 numbers have to add up to a total of 175 people. And now that I know that there's 147 with no PiPhone, if there's 110 that don't have a laptop, that means that there's a total of 37 people here with a laptop but no PiPhone, because these two have to add up to 147. Going down, I can see that there's 44 people with a laptop. I already counted 37 of them, so 7 more must be up here that also have a PiPhone. Going this direction, looks like we should have 21 people with no laptop but have a PiPhone. And then finally, this section here, I get 131 people that have no laptop. And now we see that these numbers add going side to side and they add going up and down, which makes a two-way table really nice because we can add up our totals and double check our numbers. Now the actual numbers inside of this box correspond to the Venn diagram. Laptop and PiPhone, that was the and section right here, 7. PiPhone, no laptop, that was only PiPhone, 21 right there. Laptop, no PiPhone, that's only laptop. And then no laptop, no PiPhones right here, that's this number. So what's the difference between the Venn diagram and the two-way table? Well, the big difference is over here. In your two-way tables, you will have totals for the columns and the rows. So a two-way table has totals for columns and rows. I don't know how to spell columns. I think is it only one L? I don't know. Columns and rows. Pretty sure it's only one L because it looks wrong. But whatever. Words are hard, so we're just going to move on. All right, find the following probabilities. Probability of a PiPhone or a laptop. Now, a probability is usually written as a percentage or a decimal amount. The way we find it is by looking for the favorable result compared to the total possible. So the total possible people in my survey is 175. So the probability would be, of those 175, how many of them have a PiPhone or a laptop? We already found that up here. It was 65. Using these three numbers here, that's the people who have a laptop or a PiPhone. These are the only people that do not have a laptop and do not have a PiPhone. So you could just do 175 minus 110 and get 65, or add up these three numbers together. Remember, if you're adding up the totals, you would have to subtract out the 7 because you're double counting it. So you can't just say, oh, 28 and 44. You can't do that because you're double counting these 7 people. So we get 65 here. And if you take out your calculator and type in 65 over 175, it comes out to about 37%. So that's our probability. What's the probability of having a PiPhone and a laptop? Okay, with an and, they both have to occur. These 7 people have both. So 7 out of how many? 175. So that one approximately comes out to 4% when you plug it into your calculator. All right, let's flip it over. Now we're going to talk about association. Is there an association between PiPhone owning and laptop owning? Basically what we're asking is, if you own a PiPhone, are you more likely to own a laptop or less likely to add a laptop? Are they connected? Do more people own PiPhones and laptops, or are you less likely to have one if you have the other? Okay, we're going to find this by comparing the probabilities of laptop owners. Oh, stupid lights. We're going to look at the laptop owners who have PiPhones and the laptop owners that don't have PiPhones, or the laptop owners with a PiPhone and the no laptop owners without a PiPhone. Anyways, here's what we're going to do. All right. So what we want to see is PiPhone usage changing ownage? That's not the correct word. Is PiPhone owning? I don't know, whatever. If you have a PiPhone, is it changing the percentage if you have a laptop or not have a laptop? So let's start by looking at the laptop users. There's 44 of them. How many of those 44 people have a PiPhone? 7 do. Okay, so we're looking at the laptop owners with the PiPhone. Okay, so the laptop owners, there were 44 of them. How many of them had a PiPhone? 7. 7 out of 44, if we plug that into our calculator, it comes out to 16%, about. All right, now let's look at what if you didn't have a laptop. Okay, so we're only looking at the non-laptop owners here. There were 131 of them. How many of those laptop owners had the PiPhone? 21 did. So that's what we're going to look at next. No laptop with a PiPhone. Stupid bells are off. All right, so we end up with 131 no laptop, and there were 21 of them who had the PiPhone. If you plug this into your calculator, you get, what do you know, 16% again. So what does this tell me? It tells me that if I have a laptop, I'm 16% likely to have a PiPhone. If I don't have a laptop, I'm still 16% likely to have a PiPhone. There's no relationship there. Having a laptop or not having a laptop is not affecting if we have a PiPhone or not. So there is no association here because I'm not more likely to have a PiPhone or more likely to not have a laptop. They have the same probability. So there's no association. So in here, we can say if we have a PiPhone, we are equally likely to have a laptop or not have a laptop. Next one. 145 students are enrolled in Advanced Math 8 at Granite Ridge. 116 are boys, 29 are girls, 24 are the boys, and 7 of the girls earned A's for the first semester. All right, let's fill in our numbers. 144, 45, that's our grand total. We'll put it over here. All right, 116 boys, that would be this column total, a total of 116 boys. Okay, let's look at the girls. There are 29 there. Next, 24 boys earned an A. So boy and A, that is 24. And 7 girls earned an A, so 7 girls there. Okay, now we can fill out the rest of our table because remember, everything should add side to side and up and down. So if I've got 24 boys with an A, that means 92 boys did not have an A because that adds up to 116. If there's 7 girls with an A, that means there's 22 girls without an A. Total A students goes over here. That'd be 31 A students. Total students without an A, 114. And now everything's adding up in columns and rows. So in our two-way tables, everything should add up in our columns and rows. Next question, is there an association between gender and grades? So is being a boy making you more likely to have an A, or is being a girl making you more likely to have an A? Well, just looking at these raw numbers here, it's hard to tell because there's more boys. You might look at it and go, oh, there's 24 boys. Yeah, you're more likely, but there's more boys in the survey. So instead of just looking at the raw numbers, we should look at the percentages instead. And instead of doing it kind of dirty like we did up here, let's make a relative frequency table. Now, in the relative frequency table, instead of going side to side and up and down, we're only going to go up and down. And we're going to look at percentages because percentages are going to tell us if there's an association. So looking at this first one, I'm going to find out what percentage of my boys had an A. Well, there are 24 boys with an A out of 116 boys. So 24 out of 116, if you plug that into your calculator, it's approximately 21%. Which means that there's 79% of the boys who did not get an A. All right, with the girls, there are 29 girls, 7 of them got an A. So we're going to say 7 over 29. And if you plug that into your calculator, it comes out to approximately 24%. which means 76% of the girls did not get an A. Now looking at this, now we can easily see whether there's an association. For the A students, if you were a boy, you were 21% likely to have an A. If you're a girl, you're 24% likely to have an A. So you're slightly, very slightly, more likely to get an A if you're a girl. That's what the percentages are telling us. So there is a weak association. It's not really strong. It's only a difference of 3%, but there is some difference here. So we're going to say that there's a weak association. And why is there a weak association? Because of this. The girls are slightly more likely to have an A. Oops, can't spell. Last problem. A researcher thinks there may be an association between blood type and having the DAPT genetic defect. Is there an association? Okay, here's his data below. The number is in millions. So we want to see, is the blood type changing the possibility of you having this genetic defect? So we're going to do the same thing, kind of look down. We have to add up these numbers first. Let's see, this is 0.1, 0.4, 0.68. So this is 0.68. 268 plus 31 is 299, 311. All right, so there's our grand totals. So we want to now do a relative frequency table to see if there's an association present here. So I'm just going to stretch this out to make my relative frequency here. All right, so this will be has the genetic defect, and this is not having the genetic defect. So what we're going to do now is we're going to find out the percentages. Okay, remember we're looking at it one column at a time. Of the people, now let's look at this too. You're more likely to have type O blood. That's the most common blood type. You're less likely to have AB. So we can't say, oh, there's 300,000 people here who have the genetic defect with type O. That means they're more likely to have it than these 30,000 people over here. We can't say that because we can see here that there's definitely more people with type O blood than type B blood. That's why we can't just look at the raw numbers. We have to look at the percentages. So of the people who have the genetic defect, what percent of them were type O? Well, we just do 0.3 divided by 0.68. It comes out to approximately 44%. Now we're rounding there. It wasn't exactly 44%. We're rounding. What about if you don't have the defect? Okay, so of the people who don't have it, what percent were type O? Well, you just do 137 over 311. And plug that into your calculator. And again, it rounds to about 44%. Not exactly the same, but pretty close. So here what I can say at this point is if I have type O blood, the same amount of people that have the defect, the same percentage, have 44%, and the same percent don't have it. So of all the people who had the defect, 44% had type O blood. Of all the people who didn't have the defect, 44% had type O blood. So that just means that it doesn't make a difference for type O blood. You're 44% likely of all the people who have the defect and 44% likely the people who don't have the defect. So there's no association for type O blood. Let's move on. Type A blood. We'll do the same thing. 0.28 over 0.68. I've already done the work. It comes out to about 41%. I'm rounding, but it's about that. For type A, we do 131 over 311, and it comes out to about 42%. Now, these numbers are really close. If you actually looked at the numbers, they'd be even closer than what they appear here. So again, we'd probably say, no, there's not a lot of difference there. For type A blood, it doesn't look like having the defect or not having the defect is affected by the blood. It's about the same number here. Type B blood, do the same process. You get 10% and 10%. For AB blood, you get 4% and 4%. Now, you might notice that these all add up to 99 and these add up to 100%. And the reason is because of the rounding. A lot of these numbers were under 5 to round up. So that's why we're not quite getting there. So we're going to look at this one and say it's close enough to being the same that it's probably the same. And all these numbers are exactly the same. So what we can say is there's no association. Remember, we're not comparing the numbers going up and down, because this is just saying that more people have type O blood, more people have type A than B, then fewer people have AB. Okay, so this is just the percent that have each type of blood type. What we're really looking at is comparing side to side. Does the blood type change whether we have the defect or not? And it doesn't look like it changes whether we have the defect or not. We have the same percent. Does type A change whether we have it or not? No, it's about the same. B, no, it's the same. AB, no, it's the same. So the blood types don't change whether or not we have the defect. The end. All right, see you guys later. Math hard.